We're going to continue. Genesis, can you hear me? Can you see me?
Yes, doctor, both.
Thanks. Okay, so let's see. It's a question here. Okay. Yes. Is there any way we can? It's supposed to be on the side. Jesus Christ. Okay. Can you see my projection? Can you see my projection?
Yes, doctor, but
Okay,
it's not
thanks.
full screen.
Not full screen?
No.
Now?
Yes.
Okay, thanks. So we were forming the global equilibrium equations. Here we're applying the supports. We have to recognize here that we have the same number of unknowns than the number of equations. If we want to solve it, if we want to solve it uniquely. For this step, remember, we have to go. First, we solve for the unknown displacements. And this is the way I explained you to do. But you could extract this system of equations 3 by 3 and solve it outside, but it's much simpler to just include this. Here, this is very large number, and here, equal to this large number times the value of the displacement that you want to obtain. In this case, these are zeros, so we got these 3 zeros, and the last 3 are also 0. This is the external moment in joint 2, which is also 0. So that's the solution. These 3 values should be 0. They are not exactly 0, but it is very small. E to the minus 16. In practical terms, that's null, that's 0. Similarly, for the displacement of the third joint, see, e to the minus 17, basically that's 0. And then these are the displacements that we need for this joint, okay? Moves to the right, moves downwards, makes sense. This rotates in the negative direction. So if this is the global reference system, so positive is counterclockwise. In this case, we obtain a negative, that means that it rotates in the positive sense. It makes sense. Okay, and then we multiply, and right now, this is the second subsystem, okay? This is the first subsystem here. Let's see if we can try right here. Jesus Christ. Shoot. Okay. So this is the first subsystem. And this is the second subsystem. So here we find these 3 values. And here we found this, and we found the second part, which is the reactions in the third joint. So we have 3 unknowns here. We have 3 more reactions, 3 more reactions, total 9 unknowns. That's the solution for the global equilibrium. And then what we do is we go one element at a time. Okay, for example, I'm explaining here element 2. Okay, so element 2, this is element 2. Okay, we go from 2 to 3. So this is the local reference system. This is theta equal to minus 90. Okay, let me change color. I'm going to show. I'll try. Okay, I'm going to show the global reference system, which points to the right there. Okay, so this joint here, I'm going to write to the left. It says that you move to the right and downwards. So this moves to the right and downwards. So this is D2X, this is D2Y. And now what we need to do is try to find in this local reference system, these values. Okay, oh, this is talking about element 1. It's going to consider element 1. Okay, again, let me change color again. Oh, Jesus Christ. Okay, so this example, it presents the solution for the first element. So we go, this is the X direction. This is the Y direction, local. Okay, so these two, we are going to try to express in these coordinates. Okay, so this is the T matrix. So you see that is cosine, sine, minus sine, cosine. Similar for this one. And the rotation is the same. So we take these 3 values. These are the displacements of the first joint as a vector, and these are the displacement of the second joint. These are the displacement in the local reference system of the vector. So this is 0.0 data. This is this value here. So this, it's like this. Why? Because this points in this direction. The next value is minus 0.000185. So it's like this, and this is like this. So this is the transformation that we have prepared. And now, if this ends, this joint 2 moves to the right, this element will be in tension. Okay, this is what we're saying. Okay, we apply D2X of this element. So it's the motion of this joint in this direction. So this is this. So this is D2X in the local. Since it moves to the right, this value here, the difference is positive. You see that this is positive. If that's positive, that means that the force is going to be in tension. And the stress is also. And you see that the value is very small. So we could apply a much larger force and we will be safe. Now, what else? Remember that we need to calculate the shear force. So shear force, remember it's EI sub C, the third derivative of the displacement with respect to X. And since V, this is a cubic, the third derivative is a constant. So we have that this vector is going to be this times that. So we multiply D1Y phi1Z, this is local, D2Y, phi2Z, local. Multiplied by EI sub C. So here, if we differentiate 3 times, we got a value of 12. Then the next element is this one here, 6L minus 12 and 6L. Okay. So we have D1Y phi1Z, D2Y phi2Z. So we make this multiplication, and this is the value that we obtain, 183 newtons. That's not much. That's not much. And it's constant in the element. This is for the bending moment. Remember, bending moment means second derivative. Second derivative. So in this case, the second derivative will produce a linear variation. Okay? So what we present here is the result of the differentiation. Differentiation produces, this is the second derivative of n1 with respect to x. Second derivative n2, n3, n4. And we multiply this by the d1y, phi1z, d2y, phi2z. And the result is this evaluated at each one of these points. So that's the bending moment along this element. This is a linear variation from a negative value to a much larger value at the top and here. And with this moment, we have the dimensions of the element. We can calculate the normal stress in bending, maximum normal stress in bending. And we see that the value is very small. So basically, bending is not much, okay? Basically, they are supporting axial force. Okay, we do the same for the second element, sorry. Okay, in this case, we go in this direction. So this is theta, 90 degrees negative. Sorry, here it's negative. So cosine is 0, sine is -1, cosine is 0, and minus sign is -1 is +1. So that's the transformation. So this is D2 there. So basically it doesn't move in the X direction. So this end in this direction, in the vertical direction, virtually doesn't move. Okay. This moves in the positive Y, so this is Y. So it moves like this, mostly, and rotates. Again, for this element, we apply D2X minus D1X. D2X, since this end doesn't move, it's 0. This is 0. So it's minus D1X. D1X is this value. So this is equal to that with negative, that's what you have there. Multiply by EA and you get P, that's compressive. That's compressive. Shear force, constant, bending moment, linear variation for the element. Questions about this, people? Questions about this? No, okay. Now, let's use a different connectivity. See, the way we're going to define the elements are different. So we have the same joints, but now you see that the second element here the second element here goes from 3 to 2. So the local reference system will be this. This is your X, and this is your Y. So this is going to be theta, which is going to be plus 90 degrees. Okay, so we follow the same procedure. And of course, the result has to be the same at the end. Okay, so let's do it. Element 1 doesn't change. Element 2 changes. Okay, you see here that I'm showing that this is plus 90, as we explained in here. Okay, so the sign changes. The sign is now plus 1 here. The cosine is again 0. That's the element matrix, element 1 matrix. That's element 2 matrix. Here we have the difference, okay? So remember that this matrix, okay, relates the equilibrium of 2 joints, okay? So these first three equations are related to the external forces in joint 3. In the second 3 are related to the external forces in joint 2. Okay? This is the joint 3, this is joint 2. So this is the way it should be considered. Okay? Now, this is the global reference, global stiffness matrix. Okay? How it is formed? Like this. Okay? So we separate in group of 3 because we need 3 of these equations for the equilibrium of each one of the joints, since we are considering 3 degrees of freedom. Okay? So this relates joint 1 and joint 2. So it's like saying that this is K1, 1. Joint 1, joint 1. This is joint 1, 2. This is 2, 1, and this is 2, 2, if you want. But it's not one element. It's a 3 by 3. Now here, this is K, row 3, column 2. This is K, I'm sorry, this is K33. Sorry. This is row 3, but it's column 2. This is K, row 2, column 3, this is K22. So this is 3, 3. Okay, so that's 3, 3. This is 3, 2. So you take these values and you put it into here. There. That's how this matrix is formed. Questions about this, people? Questions about this? So the resulting stiffness matrix is the same as we had before.
Doctor, I have a question. For example, we find the matrix, the element 2. Is necessary the order in 3, 4, 3, 2, the component, or we can the 2 or 3. For example.
If this is the way you have defined your element, in this case, where are we? If this is the way you have defined your element from 3 to 2, that imposes the order of these elements, of this part of the matrix. You cannot change that. So this is the order, this is the way the equations are set up. And when you recognize that, you recognize the position in the global reference system when you have to add these values. Okay? So I'm showing you clearly the two situations. when you define, first you define joint from joint 2 to joint 3. And now I'm showing you from 3 to 2. Once I define this, I have to keep track of the process following this definition. So the first equation goes with the first joint, 3. The second equation of this element goes through with joint 2. Okay, now the procedure is the same as before. So what we have to do is first, we have to solve for the unknown displacements. Okay. This is a large value. On the right-hand side, we multiply that large value times the values of the displacement that we know. We solve it, and we get the same. Second part, second subsystem is the process to find unknown external forces, and these are the reactions. Unknown external forces, that's the reactions. So we get the same values. Okay, and then we proceed. Well, in this case, it's a good idea to check the equilibrium. I'm using the connectivity too. So I have these 3. We consider for the first, these are the external applied here that we know, and these are also reactions in the other joint, which is clamped here. So in this case, this force points in the negative global x direction. That's what I'm showing it to the left. And this value, which is much smaller than that one, in the third joint, also negative, so points to the left. So we can remind, this is the global reference system like this. There. Vertical, so this one here, negative, so you see that it points downward. This one here, positive, here, points upward. And you see that to the left, I have this value, and this goes to the right. So this one cancels the combination of this and that. Now, in the vertical direction, I have this plus this, and cancels this one here. And finally, we have to include the moments. So this is a large moment when you compare it to this value. That's why I draw with a larger line here as we compare with this one here. So you set up, for example, the equilibrium here, and you can consider the moment generated by these 2 forces, the moment generated by the vertical. The horizontal doesn't have any arm. And also you have to consider this moment, and they should be in equilibrium. So that is something that we should always check. Oh yeah, I remember now. Please, these are external forces what we have calculated. Remember, internal forces, which is the next step, are related to cuts along the structure. When you do a cut, in the cut, you have to consider P, V, and MZ. Those are internal forces, axial, shear, and bending moment. That's different, please. And we're using, remember, the convention that positive bending moment, smiling face, and all of that. That's for the internal forces. Okay, so I'm going to show you the calculations for the second element, okay, which is the one which is different from the previous example. Okay, so these are the displacement of the three joints. We remember that in this case, element 2 goes from here to there. This is that. This is theta. And what we do is we transform. This is the T matrix. In this case, theta is plus 90. So cosine is 0, sine is 90, minus sine is minus 1, and this is 0. And this is the same as this one. So we have this is the 3, the displacement of the third joint. So because this is the first joint of this element, and this is the second, which is D2. We do this multiplication, and this is D3, both in the local, and this is D2 in the local. Okay, now, this is negative. That means that this point moves downward. And this one is negative. So if this is positive, you move to the right. And this is exactly what we obtained in the other case. Remember, this is local. So we establish, or we present these values in this reference system. Local is in that direction. That's your X local. In this case, the result is negative there. We proceed to the internal forces and stresses. And again, we have to recognize that the second joint of this element is, in this case, joint 2. So it's going to be minus this value here, minus this value, minus 0, because the third joint doesn't move. That's why we obtain a negative value here, and we have a compression stress. Shear force, bending moment. Questions, people? Questions about this? Questions about this? That's why it's so important to define clearly each one of the elements and then proceed with the global to local using that definition. Okay, now, this is something which is very interesting, okay? In our case, we are considering a combination. See, we have this element, and this element receives this force, okay? So this is axial force. Let me go back. That's this value here. But also, we have external forces in here. So we have this, we have that, and also we have moment. I'm sorry, in moment. Remember, these are external moments. So if we make a cut here, we have both effects. We have, because of the axial force, we have uniform stress. Let me put it up here. So we have something like this. There. And because of the moment, okay, in the same section, we have a variation, linear variation like this. So this is because of P, and this is because of MZ. So in this case, in the top of the section, you have a positive P, positive sigma. But also because of the moment, in this case, I'm just showing something, right? In this case, in the top, I'm showing an stress because of the bending, which is also positive. So on the top, we're going to have a combination of the two values, okay? So that's what we do here. In this case, for example, in this case, these are the values that we need to combine. Here, this is the stress, this is in compression, and this is the stress, okay? But along this element, okay? The normal stress because of the P force is uniform, is constant. But the bending moment changes. That means that this value also changes. Oops, sorry. I don't know if I'm okay. So what I'm showing you here is that if I make different cuts at different positions, okay? So this is the position specified by this number. So from here is 0, 0, up here is 3. Okay, so at different position, we have this value of the stress on one side and this value of the stress on the section. This is uniform. So you have to combine along the. Questions about these people? Questions? In this case, what we do is we simply add.
I have a question.
Yeah.
In the two elements of being the value of P is more larger or more critical than the values of stresses in the table of when we calculate the moment.
You cannot generalize. You cannot generalize. In some problems, the area will be large. In some problems, the inertia will be more important. And in that case, you will have either one effect, which is more important than the other. That's your job. That's your job. See, if, for example, you recognize that one element develops a large value of P, that means that the area of that element should be increased. If you recognize that one element is working in bending, that means that the inertia of that element should be increased in order to reduce the normal stress because of the bending. You cannot generalize. You have to simply do an analysis. And in some cases, by inspection, you can recognize what elements are working in tension or in aligned force, and what elements are working as beams, right? Bars or beams. But in general, you have to do the calculation and then conclude which one is which.
My question is about the P value is related to the bar element or bar case.
Yeah.
So
Yeah.
my question is,
here you have P, here you have MZ.
so in that case, both elements have I don't know,
A variation?
have variation of like a beam or
Yeah.
some.
So if we analyze this, let me change color. Let me try to change color, okay? The other element was from here to there. That's your X, that's your Y. And we can do exactly the same. We can do cuts. Now, in this case, the axial force was positive because this force moves to the right and put this element in tension. But the bending moment, again, depends on X. So you make different cuts and you see a variation in the bending moment. And according to the variation of the bending moment, you have to calculate the maximum normal stress because of this bending. And in that case, you have to add in the side where the stress is positive. Why? Because in that size of the section, that stress, which is positive, will be combined with this value or the stress from this value, which is also positive. So in this case, let's suppose that we have something like this, okay? We have tension because this force is positive, but also you have to combine with the moment, Okay, so probably you're gonna have something like this, tension here. Okay, so you see that on this side of the section, you have positive stress. And also here you have positive stress. So you have to combine, because in that region, see on this side of the element, there's the possibility of failure reaching 235 in the case of steel. Yeah, you have to do this analysis for every element. But please remember, this is something that we're going to see in when you do ANSYS analysis. Right here, let me try to identify where is my pen. Let me draw with. Color. Okay, so this is the section, okay, and we have this. This is normal stress. Jesus Christ. Because of P. And we have to add normal stress because of bending moment. And you see that if I ask for the value here of the stress here, for example, let's call it this at the top. So here at the top, we're going to have this value, which is positive, minus this value, which is negative. Here, Isaac, are you there? Isaac?
Yeah, doctor.
How do you call this? It's a mid thickness or a mid plane, right? Do you remember mid plane? Okay.
Yeah.
And here, this is the bottom. So you have three values. So in general, especially when we work with plates, okay, you say, okay, I need the stress. Where? At the top, mid plane, or at the bottom? And you see that at mid plane, basically, you consider only the stress because of the axial force. At the top or at the bottom is a combination. This is an exercise we did in shear structure. When you have a value of stress up here and a value of stress down here, if you do the subtraction and divide it by 2, you can obtain the value of the stress because of bending. If you add and divide it by 2, then you have the stress because of the axial force. Any more questions, people? Any more questions? No, okay. Before we go to the break, people, yesterday I was trying to load this report, SNAME report, where we have this example to analyze. But for some reason, I could not load it in the Aula Virtual. So I loaded in the Teams platform. So I ask you in these few minutes before we continue to check the Teams platform and download the report, because I'm going to refer to that in a few minutes, okay? And that we're going to do that when we return.